Let's recap the exponential distribution. So we said that an exponential distribution has a shape that looks something like this. So let's say we have an exponentially distributed random variable y. Okay, here is f of y up here. This is the probability distribution function. And we said that the shape of this thing looks something like this. Okay, that is, first off, it's truncated at 0. We can't have negative realizations of the random variable y. And it decays as y increases, and it goes out indefinitely in the positive infinity direction. Okay? We said that the shape, the appearance of this curve is governed by one parameter, and that parameter is called lambda. Okay? We said that lambda was the same parameter we talked about with the Poisson distribution. It is some rate of occurrence. Okay? The rate of occurrence of events. So that could be occurrences per some interval. Okay? We said the Poisson distribution allowed us to count the number of occurrences in some interval. The exponential distribution allows us to calculate the interval until the next occurrence. So there's a relationship between the discrete Poisson distribution and the continuous exponential distribution. Okay, so what does this distribution look like in equation form? F of y, the PDF is lambda e to the minus lambda y. Okay, so this curve is lambda e to the minus lambda y, where lambda is our rate and e is just Euler's number. Okay, so if we wanted to find the value of the probability between a and b of random variable y, that's the area under the curve between a and b. That's the integral of the PDF evaluated between a and b. This is the probability that y takes on a value between a and b. Okay, so what is that? We could just integrate that if we wanted to. That is the probability that y takes on a value between a and b. That's the integral from a to b of this function, lambda e to the minus lambda y dy. Okay? Another way we could calculate this probability is by using the cumulative distribution function. Okay, the cumulative distribution was this, you might recall, in general, capital F of y, the cumulative distribution, is the integral between the lower bound of the distribution, in this case 0, up to the value y of the PDF, little f of y, which is lambda lambda e to the minus lambda t dt. Okay? If we do this, if we work our calculus magic, we get that capital F of y, the cumulative distribution, is 1 minus e to the minus lambda y. Okay, that's the cumulative probability up to the value y. So to find this area, we could use this cumulative probability. Okay, this area right here, let's just rewrite that. The probability that y is between a and b is this area. Let's do it here. Here's b. Okay, this entire area between 0 and b. If we subtract off this area, the probability between 0 and a. Okay, take this bigger area, subtract off this smaller area, and that leaves us with this. Well, the big area is the cumulative probability between 0 and b. That is capital F of b. And this area right here is the cumulative area, the cumulative probability between 0 and a. That is capital F of a. Okay, so that difference gives us this area right here. Okay, so this is an important property of the exponential distribution. Okay, knowing this formula right here allows us to calculate any different range, any different interval along y.